Hi, I'm George Woodbury from College of the Sequoias in Visalia, California, and in this video we're going to solve exponential equations that are different than the ones that we've seen before. In the past, instead of 5 to the x equals 20, we may have seen something like 5 to the x power equals 125. And we could solve that by rewriting the right-hand side in terms of the same base, 5 to the third. Using the one-to-one property of exponents, we know that if these two expressions with the same bases are equal, then the exponents must be equal. But in this first problem, we cannot write 20 as a power of 5. Also, another strategy we used was to try to change the base on both sides to be the same, but 5 is prime and that can't be broken down anymore, and 20 is cannot be expressed as a single base to a power. 2 times 2 times 5. It has different prime factors. So what we can do, and I'm going to show you a couple of ways to solve this one that will reinforce some of the things we learned about logarithms, but the best way to solve this one is by taking a logarithm of both sides. And you want to try to take a logarithm that's on your calculator. So unless I see a base of 10, I'm going to use the natural logarithm. So my first attempt at solving this, I'm going to rewrite the problem, 5 to the x power equals 20, and then I'm going to take the natural logarithm of both sides. Now I can use the power rule, and that's why we take the logarithm, to rewrite that exponent x as a factor. So now we have x times the natural logarithm of 5 equals the natural logarithm of 20. And we can solve by dividing both sides by the natural logarithm of 5. So x equals the natural logarithm of 20 divided by the natural logarithm of 5. And that is the exact solution. We're also asked to round this to the nearest thousandth. So we'll go to our calculator to approximate this logarithm to approximate this ratio of logarithms to 3 decimal places. So I'm going to use the Desmos scientific calculator. And to get to natural logarithm, I tap on Functions, Natural Logarithm. It's over here in the right side batch of buttons in the first column, just above e, just below e to the x. So that was natural logarithm, back to the main 20, tap outside the parentheses, divided by, and now we'll do the natural log of 5. Function, ln, main, 5, enter, and to 3 decimal places, that's 1.861. Oops, sorry about that. Now, we could do a quick check to see if we're in the ballpark by raising 5 to that power. Now, we're not going to get exactly 20 because we rounded this to 3 places, but we should be close to 20. So the check, we want to see if 5 to the 1.861 power is close to 20, and we can do that on the calculator. 5, the exponent key, 1.861, and on the right-hand side we see 19.9886, pretty close to 20, and the more places that we use from our first solution, the closer that's going to be to 20. Now I mentioned that there is more than one thing that we can do. Another thing that we could do that's not the most efficient, and let me change color for this, is to rewrite this as in its logarithm form. And so the logarithm form is log base 5, because 5 is the base. The arguments on the other side of this equation of 20 equals x. So we're kind of in a weird spot here because I don't know how to do log base 5 of 20 because I didn't know how to do 5 to what power is 20. However, we can use that change of base formula that we learned about and rewrite this as natural log of 20 divided by natural log of 5, which is what we had over here. So it shows that there are a couple of ways that we can go about solving this one. I think the method on the left is a little more automatic, but the method on the right is not bad either, and it's a way to show that you really understand the concepts of logarithms. However, I'm going to continue to use the approach on the left side because it will work with more equations than the one on the right will, including the one that we're about to do here. What makes problem 2 more challenging is that we have x, the variable, in exponents on both sides of the equation. And so this one would be tough to rewrite in logarithmic form. However, we can solve it by taking the logarithm of both sides. So we've got 3 to the 3x minus 2 equals 7 to the x plus 1 power. And so I'm going to take the logarithm of both sides. Natural log of 3 to the 3x minus 2 power equals natural log of 7 to the x plus, to the x plus 1 power. Now we'll apply that power rule, but because it's not just the single term x, we're going to bring that exponent down in parentheses. Parentheses 3x minus 2 natural log of 3 equals parentheses x plus 1 natural log of 7. This last part of solving is going to look similar to when we were doing the inverses for rational functions. We need to do all the distributing, then we'll collect all the terms with x in them on one side of the equation, everything else to the other. We'll factor out the common x, and then we'll solve. So 3x natural log of 3 minus 2 natural log of 3 equals x natural log of 7 plus 1 natural log of 7. And that 1 we don't really need. I need to get all the terms with containing x to the one side. I'm going to move them to the left. So I'm going to subtract this one over to the left-hand side. And I need all the terms without that variable x in them on the other side. So I'm going to add 2 times the natural logarithm of 3 to both sides. And what I'll end up with is 3x natural log of 3 minus x natural log of 7 equals natural log of 7 plus 2 natural log of 3. So again, subtracted x natural log of 7 from both sides. So that ends up as a subtraction there. And then we added 2 natural log of 3 to both sides. So that ended up as a sum. Next step, I want to factor out the common factor of x on the left-hand side. So x times 3 natural log of 3 minus natural log of 7 equals natural log of 7 plus 2 natural log of 3. Divide everything over to the right-hand side to solve for x. So I'm going to get x equals natural log of 7 plus 2 natural log of 3 over 3 natural log of 3 minus natural log of 7. And that's my exact solution. Now I'm going to be able to clean that up a little bit. I'm going to show you how to do that. We can condense logarithms, and we can condense those 2 logarithms in the numerator into a single logarithm. Remember that this 2, by using the power property in reverse, can become an exponent. So that's going to be the natural log of 3 squared, or 9, because we're adding the natural log of 7 to the natural log of 9. We have that property that allows us to multiply those arguments. So this becomes the natural logarithm of 63. 7 times 3 squared. In the denominator, 3 times the natural log of 3 is the same as the natural log of 3 cubed, or the natural log of 27. And because we're subtracting those, I could rewrite this as the natural logarithm of 27 sevenths. Now, am I saving some work there? I'm not so sure. Getting that numerator into one logarithm of a single argument, an argument that's a single number, is a plus. But in the denominator, getting that into the calculator, it's a little more challenging than the numerator, but it's about equivalent to the denominator I started with. And so we may wonder, did we need to do that? All right, so I'm going to approximate these, and I'm going to start with the first one. I'm going to start with ln7 plus 2ln3 divided by 3ln3 minus ln7. Function, actually, let me go back to the main. I need a fraction, and in the numerator, function function natural log, that didn't work. I got to get into the numerator. Natural log of 7 plus 2 times function natural logarithm of, back to main, 3, divided by 3 times function natural logarithm main 3, tap outside, minus function natural logarithm main 7. And so to 3 decimal places, this is 3.069. Let me write that down before I forget it. Oops. Now let's try the other one. We've got the natural log of 63 divided by the natural log of 27/7. We'll do a fraction. Function ln main 63. Tap in the denominator. Function natural logarithm back to main. Fraction, we had 27/7, and look what we have there, 3.069. So a couple of different ways to come up with that approximation. You need to decide which way is easier for you to get it into and out of your calculator. In that numerator, there were definitely some pluses. It's easier to do natural log of 63 than it is to do natural log of 7 plus 2 times natural log of 3. The denominator, at the very worst, what we could have done is this. Let me try it one more time. Fraction, function, natural log, main 63. In the denominator, I could have done that difference of natural logarithm of 27, tap outside there, minus natural logarithm of 7. And that wasn't so bad to enter. So if entering that fraction gives you a little trouble, you could have left that as a difference. But it's easier to use natural log of 27, I think, than 3 times natural log of 3. All right, so we came up with the same solution there, same approximate solution, 3 different ways. 3.069 is the approximate solution. And again, if you want to check that, we haven't done anything that will make an extraneous solution. But if you want to check to see, are we close, you can put that 3.069 in for x way up at the top and see if the two sides are the same. Let's see. 3, and I'll write this here in a different color. Check. 3 to the 3 times 3.069 minus 2. Does that equal 7 to the 3.069 plus 1 power? And probably easier to simplify the exponents on both sides. On the left-hand side, if you do 3 times 3.069 and then subtract 2, you get 7.207. On the right side, adding 1 to that number gives us 7 to the 4.069. And then you could just evaluate both on your calculator to see if they're close or not. All right, that's the end of this video. I'll see you in the next video for more exponential equations to solve.